So now we're going to talk relativistic laws of motion. And we're going to start off with momentum. Remember, momentum P equals mv. That's the classical version. But one of the other things that changes when an object's in motion is time dilates, length contracts, and mass increases. So as something is going closer and closer to the speed of light, its mass is going to increase. So instead of just being able to use this, we have to take into account the mass increase. So for using Einstein's special relativity, P is going to equal gamma times mv. And that basically is saying how much the mass is increasing. And if you actually work it out using gamma, the reason why you can't have anything travelling at the speed of light, if you look at this equation, 1 is equal to, the gamma factor 1 is equal to 1 over minus v squared over c squared. As this becomes, if this were travelling at the speed of light, v would be equal 1, c would equal 1. 1 minus 1 is 0, square root of 0 is 0. 1 divided by 0 is, your guess is as good as anybody else's at that point. So that means anything with mass, as it approaches the speed of light, it can approach the speed of light, but to actually travel at the speed of light would probably take an infinite amount of energy. So, talking of energy, how much energy does it have? Well, the classic formula for K is equal to half mv squared. So let's put a relativistic. The classic one is EK is equal to half mv squared. That's the Newtonian laws of motion. And we're going to have something similar to this as well. For relativistic, E, the energy is going to equal the gamma factor times the mass times the speed of light, speed of light squared. Which we can also call it a relativistic, the relativistic kinetic energy, which is strangely enough going to be a negative number, plus mc squared. So this is if you're going at relativistic speeds. So if you're going a fair chunk of the speed of light, so as I said, even with something, Mercury, for the planet Mercury, even 50 kilometers per second is enough where this may come into effect at some point. So what is K? It's K. So K is going to be our relativistic energy. So K is going to equal gamma times mc squared minus mc squared. And remember, because, so basically, which is equal to gamma minus 1 times the mass squared. Okay, so anyway, maybe that's not going to be a negative number. That's going to be a bloody big number, isn't it? I apologise. Okay, so notice we've got this extra bit here, this mc squared. What's that mc squared all about? Well, the mc squared, this is the classic special relativity. This is probably the most famous equation in the world. E is equal to mc squared. And that's going to be the energy of an object, and that's going to be at rest. So when the object's not moving, times the mass of the object, times the speed of light. Right. So mass is going to be in kg, this is going to be in meters per second. So you end up with kgs meters squared per second squared, which is going to be joules. Now, how much energy is there in mass? Well, if you sit down and work this out, one gram of energy, so 1 gram, how much energy in 1 gram of matter? Well, let's say 10 grams of matter. Because if I remember rightly, there was this book about oh, what was it, Angels and Demons or something, where somebody steals some antimatter and annihilates. And basically what would happen is you'd end up with several grams of matter disappearing, would turn the mass into energy. How much energy is in 10 grams of matter? So E equals mc squared, which is equal to 0.01 kgs times 2.998 times 10 to the, what's that, about 10 to the 8 meters per second squared, which is equal to 0.01 times 2.998 exponential 8 squared equals 8.988 times 10 to the 14 joules. Is that a little or a lot? Well, let's find out. If we were to convert that into kilograms of explosive, say TNT, that's about 4.7 kilojoules per equals 1 gram of, so what's that, 4.7 megajoules divided by that, so that's going to be equal to, engineering, that's equal to equivalent to about 191 million tons of TNT. That seems a little high. Okay, sorry, 1,000 tons, 1,000, sorry, my apologies. That's equal to 191,000 tons of TNT. So in other words, that is actually quite a lot of energy. And what happens when a nuclear weapon goes off? Basically it turns matter into energy. Not very efficiently. This also happens in nuclear reactors, that when you have a nuclear reactor, the energy comes from the fact that you turn some of the mass in the nuclear material into energy. Okay, so anyway, what is K? K is that. Okay, so most famous equation. So what about if we have particles with no mass? So we can say E squared is equal to momentum squared times C squared, all squared, plus mc squared squared. That's another way of working out the energy. You basically take the momentum, which we worked out there. I should put a little twiddle under that, so it's momentum. And then we had the mass times the, so we add the rest energy as the matter. So, but what happens now? What happens if that particle has no mass? If m equals 0, and you'll probably go, no, you can't have stuff without particles without mass, without a rest mass, and the answer is, well, you can. I mean, a photon traditionally has no rest mass, it has no mass, so the energy in a photon, energy squared, is equal to pc squared, so energy is equal to the momentum times the speed of light. So you can have particles with zero mass, like a photon, but does have momentum. And this is actually how light sails work. I don't know if you've ever heard of light sails, but the idea is you put out a large sheet of mylar, you hook it up to your spacecraft, and then the sunlight pushes that around. So the photons of light from the sun, you push that around. Doesn't give you a lot of acceleration, but in theory it gets you around the solar system. So let's do a couple of exercises. Let's do exercise 7.3. What is the rest energy of a proton? So basically, for the, using special relativity, we go E equals mc squared. That's going to be our equation, mc squared. So we know what the speed of light is, so we need to know what the mass rest of a proton is. That should be on your formula sheet. So M for mass for proton is 1.6728 times 10 to the negative 27 kg. So we just plug that into our formula. So equals 1.6728 times 10 to the negative 27 kg times the speed of light, which is 2.998 times 10 to the 8 meters per second. Square all of that. And then, as they say, it's calculator time. Dong. Okay, so 1.6728 x minus 27 times 2.998 x 8, and then we square that, equals, I make that as 1.5035 times 10 to the negative 10 joules. Now is that little or a lot? Well, on the macro scale, our size, we wouldn't even notice that. However, for it down at the atomic scale for a proton, let's check. Let's convert that to electron volts. Just convert to electron volts to EV electron volts. So energy in electron volts, energy is going to equal 1.5035 times 10 to the negative 10 joules divided by the elementary charge. So EV volts equals energy divided by the elementary charge. So elementary charge is what? 1.602 times 10 to the negative 19 coulombs. Well, yeah, I suppose you can. Yeah. Okay, so anyway, multiply it by, which is equal to, so we go 1.602 exponential negative 19 equals, let's convert that into engineering form, 938.5 mega electron volts. Now, is that a lot of energy for a particle? Well, let's put it this way. One electron, a UV ray has 1 electron volt, and if that hits you, it can cause damage to your skin cells. So 1 electron volt's starting to get quite energetic. So yeah, when you're getting up into mega electron volts, that's got a fair amount of zip for one proton, or a fair amount of energy. As I said, if you have enough of them, you get a big boom. Okay, so let's try another one. So let's try exercise 7.4. 7.4. What is the total energy? The total energy of the proton at point 0.9 C. At 0.9 C. How, so what's that? So basically we can work out the total energy. So E, in this case, is going to equal gamma mc squared. So we know what mc squared is. We worked it out just up here. This is mc squared. It's nothing to do with music or musicians. So what we need is the gamma. So gamma is going to equal 1 over the root of 1 minus b squared over c squared. Remember, we always do this in terms of speed of light because it makes it a lot easier. So that's equal to 1 over the root of 1 minus 0.9 squared over 1 squared. Again, calculator time, so we stick that in the calculator. So 1 minus 0.9 squared divided by 1 squared. Take the square root of that, take the inverse of that, equals 2.294. Cool. So that should be dimensionless. So what we go, so E is equal to 2.294 times 1.5035 times 10 to the negative 10 joules. And so times 1.5035 x minus 10 equals 3.449 times 10 to the negative 10 joules, which as you notice is actually more. So when it's moving, it's got a component, it's got its rest energy, and then it's got the kinetic energy of the motion as well. So, and in this case, because it's going so fast, this is becoming relativistic. The mass of the the protons actually increasing. If you'll notice, in the answer, it says 3.46 times 10 to the blah 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 on the sheet. If we see this, if you're doing a test or something and we see that we're out at about the third figure here, what that means is we probably rounded in different places. And if you're doing a test or an exam and we notice that you're out at about the third or fourth place, we'll just go, oh, you rounded differently, full marks to you. So remember, in a test or an exam, we're trying to see that you understand the process, what's happening and how to do it. And if it's just third significant place, it's just a rounding difference, so we're not going to worry about that.